Welcome back. Today I'm doing an experiment and I don't know what the results are going to be, so everyone come along for the ride. So last time I showed off the beginnings of my breadboard synthesizer project with its oscillator, amplifier, and envelope generator and its ability to make some reasonably pleasant musical sounds. One of the things I mentioned at the end of that episode is that I was kind of interested in maybe creating a sequencer for it or maybe hooking it up to my 6502 breadboard computer. But I thought a good place to start with that and an easy way to prototype some things and do some experiments would be to try to hook it all up to an Arduino first. And I thought that would be a nice simple project. I thought I had some DACs, some digital to analog converter ICs around that worked on SPI or I2C interfaces that I could just hook up to the Arduino and be off and running. Apparently, though, I don't, or if I do, I've misplaced them. So what can we do instead? Well, there are other ways of getting an analog or kind of sort of analog signal out of an Arduino. The Arduino, of course, does have actual analog inputs. For example, I've got a potentiometer hooked up to this one, and it can read the values as they go. The Arduino does not have actual analog outputs. Instead, what it has are pulse-width-modulation outputs. And basically that means that it produces a square wave with a variable duty cycle. And so it's not an analog signal, it's not actually at any particular voltage that you desire, but what it does is that it changes from 0 to 5 volts frequently, and it kind of averages out into the voltage that you're looking for. And people use this all the time to control the brightness of LEDs or to control the speed of motors. But motors have a lot of inertia to them, and LEDs, well, most people can't really see much faster than 60 frames a second. But if you're talking about audio, then you have signals that are changing anywhere from 20 times a second to 20,000 times a second. And those are the extremes. What we're really talking about probably are hundreds or thousands of hertz for a lot of the sort of the musical range. And the speed at which the PWM pins in the Arduino can change is something like 480 hertz, which is awfully big compared to the length of an individual wavelength of an audio signal. So I'm kind of under the assumption that just hooking up the PWM directly to the pitch CV input of the synthesizer is not going to do what I want. But I am kind of hoping that it will do something interesting sounding, like make some weird, strange noises. And there are some things that we can do about that. I've done some research. We'll try a few things and we'll see what works and what doesn't work and so on. So to start with, I've got my Arduino. Well, this is a SparkFun Red board, which is an Arduino Uno clone, basically. And I have the potentiometer hooked up to one of the analog inputs. And I've got a little program running on it that is constantly reading the analog input and sending that same value out through one of the PWM outputs on pin 3 here to light up an LED. Now, one interesting gotcha here is that the values that you can read using the analog read function in the Arduino SDK are in the range of 0 to 1023. The values you write out to the PWM pins using the analog write function are in the range of 0 to 255. So I'm reading a value, I'm dividing it by 4, and then I'm sending it to the PWM. And for the LED, this looks mostly fine. Now, I don't know what you can see on the video yet. We'll find out. For me, the very low values, I can kind of see a tiny bit of flickering, I think. But most of that goes away at the higher frequencies, or the higher values. So now I have this line that's plugged into the pitch CV input for the oscillator. And let's take that out of ground and we'll plug it into the PWM also right here. And we're just going to send the raw unfiltered PWM into the oscillator, and we'll see how it behaves with it. So we just need to turn up the volume a little bit. And so far this is basically at 0, so it's not having any effect. But as we turn the potentiometer, whoa. Oh. Okay. I wanted some cool noises and I think I got it. Okay. All right. Wow. That was that was neat. Yeah, so that definitely did not work in terms of giving us like a smooth control over the pitch that we could use to play music or anything like that, but those are some neat sci-fi sounds, I will say that much. So I pretty much expected that not to work right away, not to give me what I wanted. I have done some research online and I've seen a few sources that say you can put a low-pass filter onto the PWM line and smooth it out and get something that's a little more usable. And the values that I've seen cited in a couple places are to build that filter out of a 1000 ohm resistor and a 0.1 microfarad capacitor. So I thought we would start by trying that and see if that does the trick. So I'm just going to hook those up real quick here. So low-pass filter is really just that. It's a resistor and a capacitor, and we have to move the input so that it's actually getting that value. So it goes right here between the two. And now we can see if that's going to make any difference. So at 0, again, we're normal. Yeah, that didn't make a whole lot of difference, I don't think. And I was a little curious about that because I put these values into a low-pass filter calculator that I found at DigiKey, and that suggests that this is a low-pass filter with a cutoff of about 1500 hertz or something like that. And that doesn't seem helpful because, like I said, the PWM from the Arduino should be changing at about 480 hertz. So it seems like we need a filter with a lower cutoff, like a lower frequency cutoff. So one way we can do that is to change the resistor value here. And it's kind of a linear thing. So this is a 1K resistor. If I put in a 10K resistor, that should cut this down to like a 150 hertz. That should be plenty. So we go from brown, black, red to brown, black, orange. And yeah, I know I've got everything hooked up and the power hooked up and I'm plugging in, unplugging things, and that's probably not a great idea. Don't do this at home. Or do, but just be prepared you might break something. Get that in the right place. Yes, okay. All right, this is what, take 3? I really like what it sounds like right about there. Anyway, that's still not what we want, but that does actually sound quite a bit closer. It's definitely not a smooth signal. There's a bunch of different frequencies that are happening in the output, but it's a lot closer than the last version was. So, wonder what we could do about that. I think I have 2 choices here. I can either change the cutoff frequency again, or I could add a second stage to the filter, because this is a single passive filter stage. I think cuts the filter frequency down by 3 decibels, which isn't really a lot. And if you add another filter stage, that would cut it down by, I think, another 3 decibels. So that might help. Let me get out some more components so we can try that. Okay, now we have 2 stages, each using a 10K resistor and a 100 nanofarad capacitor. Well, that sounds quite a lot better, actually. There's still some interesting overtones. It's not perfect, but that's a noticeable improvement over the previous version. I think I'm going to change the cutoff frequency for the filter one more time. So these are 10K resistors. I also got out some 33K. So let's try swapping those out, and we'll see what happens. Okay. 33K. Oh. That sounds pretty close to what I'm hoping for. Okay, sorry for all that time at the very high frequency pitch there. The thing is, I'm not sure that frequency is as high as it was before, which would mean that the voltage that we're getting out of this array of filters when the dial is all the way to the right is not 5 volts, which I kind of want it to be. I'm gonna check that with my multimeter here. I don't know if you're going to be able to see that, but and I'm not sure if I can get in here very well to check these voltages. I've got all the way to the right, and oh, that should be ground. And that should be... Yeah, so it's all the way to the right, and I'm only measuring 2.79, 2.8 volts on the output. So we're losing a lot of voltage to this filter. Now, why would that be? Here we're running into the limitation of my limited understanding of analog electronics. Because it's easy, especially if you're sort of a software or digital logic kind of guy like me, to think of, this stage, then this stage, then this stage. But the truth is, all these things are interacting with each other. Plus, you've got the result of the filter coming out here into the oscillator and going into a bunch of other things up here before it ever sees the inverter that powers the oscillator or the op amps. So a bunch of things could be interacting here in ways that I don't really understand, that are limiting how this is working for me. Now, one thing I might try to do is maybe buffer the output of the filter before it goes into the oscillator, just to keep anything over here from interfering with the operation of stuff over here. I don't know if that'll make a difference. I think I have another op amp somewhere that I could use for that. The thing is, for the things I want to do and the reasons that I want to put an Arduino in here in the first place instead of just doing a completely analog voltage-based sequencer thing, like what they call like a baby 8 sequencer, is so I could do interesting things with the voltages. But that requires me to have a good sense of what the relation is between my pulse width modulation output here and the final voltage that's going into the VCO, and how that's going to vary as we twiddle our knob here. Yeah, this might be awkward in terms of getting the power lines where I need them, but I'm going to try to hook up an op amp and see if having that in there makes any kind of a difference. Okay, I think I got this right. I have the output from the filter going into the non-inverting input of this TL074 op amp, which is hooked up as a non-inverting buffer, and the output of that then is going into the oscillator. So I guess we have to turn up the volume and see what happens. That sounds much higher pitched. Hold on. Turn down the volume. Tell you what, we're going to put the clips on the multimeter so that we can actually get those values. Let's see how the output. So, ground, that's the black one. There we go. And we got, you see that? .8 volts. That's much better. I might almost be starting to get the hang of this. Yeah. So now we have a range of hopefully 0. 0. Okay. To now 4 point something. This says, okay, 4.78. That's really encouraging. Okay, I think there are some things I can do with this now. I need to think about this a little bit and write some software. But I think we might actually be in good shape. And we'll see if we can do a test and see if we can actually control these things in a way that is useful and interesting. I want to be able to make musical notes. That's been the point of this the whole time, obviously. The oscillator is set up for a 1 volt per octave scale, and so I need to find some way of translating my 0 to 255 here into voltages that it will recognize as actual music notes on an actual musical scale. And I'll probably put in an insert of me trying to talk about music theory, which I understand even less than I understand analog electronics. Okay, so here's what Past Me was trying to explain. In order to produce actual musical notes, I need a bunch of different things to line up just right. First off, there's the value that we set for the pulse-width-modulation pin on the Arduino, and that has a value ranging from 0 to 255. That controls the value that the voltage that the PWM pin is going to try to emulate with its variable duty cycle, ranging ideally from 0 volts to 5 volts. Now, as we saw a little bit ago, we're not actually getting all the way up to 5 volts, but we'll worry about that in a moment. This voltage gets fed into the VCO, where it produces a tone using a 1 volt per octave translation. So we can tune the VCO so that 0 volts is a note like this C3 at 130.8 hertz. Then 1 volt up from that would be C4 at 261 hertz, all the way up to C8 at 4186 hertz, which is that very shrill, high-pitched sound. And inside of each octave, there are 12 semitones. These are the actual notes, the C sharp D, D sharp E, etc., that get you all the way back up to the next C. Now, the frequencies increase exponentially, which is tricky to deal with, but we don't have to worry about that. The VCO is going to take care of that. We just have to worry about these voltages, and the voltages are linear. It's a 0.08333 volts from one semitone to the next, no matter where you are in this scale. Now, with 5 octaves, we have 61 semitones that we're trying to reproduce because we include the C's at both ends of the range. And we have 256 PWM values that we can use to try to hit them. Now, the problem is one of resolution, and because 256 is not divisible by 61, so our PWM values are not going to line up very well with the notes that we're trying to create. And some of these notes, the closest we'll be able to get to them is like halfway between one PWM value and the next. So that's probably not great. One way we can deal with that is to turn the whole problem around. We'll start by picking a mapping from the PWM values to the CV values that we want to create, the control voltages that we want to send to the VCO. And then we'll try to figure out how to make all the voltages fit into this. So, for example, if we just want to say that the PWM values 0 through 60 are going to map directly to the semitones from C3 to C8, then every PWM value in here is going to map exactly to a given note. But what if we want to be able to get some sound that's in between notes, like if we want to do a gradual change from one to another? So maybe we won't do it exactly this way. So instead, I'm going to separate each semitone by 4 PWM values from the one before. So we still start at 0, but then this C sharp will be 4, this will be 8, 12, and so on, all the way to 240 at the end. So we're using almost the entirety of the range that we have for these PWM values. Now, the only problem is that for this to work, we need to change the voltage range so that when we output a PWM value of 240, that's actually giving us 5 volts. Currently, 255 is giving us 4.8 volts, so 240 gives us about 4.5. And the way we can fix that is by adding some amplification. So this is what the current final version of this circuit looks like, and most of this you've seen already. This is the potentiometer that we're reading values from up here, and then this section from here through here is how we're taking the PWM values out of the Arduino and conditioning them to feed them into the pitch CV of the voltage-controlled oscillator. So here's the LED that we started out with. Here are the two stages of passive filtering. And here's the op-amp buffer that we just added. And now there's one more thing that we're going to add, and it's this second op-amp that's configured as a non-inverting amplifier. And it's just going to increase the strength of that signal by about 12% so that our 4.5 volts becomes 5 volts. And I have a potentiometer up here that we'll be able to adjust to hopefully get pretty close to the value that we want. Now, I'm probably not the best person to explain how an op-amp amplifier works, but this is actually very similar to just the buffer here, which just uses a simple feedback thing to try to copy this voltage to this output. In this case, we have a voltage divider here with these two resistors, and that forces the op-amp buffer to work a little bit harder and increase the voltage on the output so that the feedback cancels out the way it's supposed to, or something like that. So now we can go back to past me, who's going to try adjusting this potentiometer, and we'll discover whether this works or not. So I have changed my Arduino program so that instead of following the potentiometer here, which is now not doing anything, it's just outputting a constant 240. And I have over here my original op-amp buffer using one of the 4 op-amps on this chip that produces at 240 about 4.53 volts. And then I've used another one of the op-amps on this chip to produce an amplifier. So we're going to try to amplify that from 4.53 to a nice even 5. And I am probably not the best person to explain how op-amp non-inverting amplifiers work, because I was very confused about it before, but I think this is correct now. But now I have to see if I can actually make this adjustment and get from 4.53, I think you can see that on the phone, on the camera, to 5. And just hold it steady here, because I've got this little 10K potentiometer here, and if I turn it just so, I really wish I had. Okay, 5. Uh-oh. Yeah, I wish I had a proper trimmer in this size. 4.98. I don't know how accurate that is or how stable it's going to be. Okay, I'm going to try to hook that up to the oscillator. Yeah, it's not very stable here. Also, this is not my best breadboard. It's kind of a pain to work with. Okay. We have an ear-piercing screech, which I'm going to assume is 5 octaves above middle C. Although I also think it's picking up some noise from somewhere. Now the question is, can we produce anything that sounds like music? So I'm going to try to write something real quick on the Arduino that will hopefully be interesting. Okay, I've calculated out some values, and I think I have a program that will play a major scale. So right now, the Arduino is still stuck at a value of 240, which is calibrated to 5 volts. Hopefully a value of 0 is calibrated to 0 volts, And hopefully that relationship is going to be linear. If it's not, because of all the analog filtery nonsense going on here, then none of this is going to work. But I'm going to compile my program and send it. And you can see the voltage numbers changing as it's running, and if we turn up the volume, hopefully we hear something. Okay, well, since this whole universe is kind of poorly calibrated and only kind of sort of in tune, that's actually kind of sort of working. I mean, it's more in tune than I could sing, so that's got to count for something, right? All right, so let's review what we've got here. Now, actually, let's try one more thing. All right, one more program, and let's see if this works. You can tell that the filter is still not perfect, but what I've done is turn back on the part of the code that reads the potentiometer and outputs that value. But after dividing the potentiometer value by 4, I'm also zeroing out the lowest 2 bits. And basically that means that as it increases, it'll increase in jumps of 4, which correspond to half steps. Okay, let's try that without the sound going on in the background. It's pretty sensitive right now, so let's turn that down a little bit. I think this will work. Okay, so I just divided the value a little bit more, kind of cut down the range. It'll only go to like 2.5 octaves right now, but honestly, who needs that shrill, ultra high pitched 5-octave sound anyway? But that makes it a little bit easier to actually control the potentiometer. So what we've got here is basically a cheap and dirty quantizer. It takes the analog value from the potentiometer and converts it into the nearest actual musical tone in our scale. Well, in a chromatic scale anyway. With maybe a few wonky spots here and there where you can get stuck in the middle maybe. So right about that point it started raining really heavily, and the rest of the audio from that recording is not very good, but I think you get the point. What we've put together is a pretty good prototype of what you need to build an Arduino-based sequencer with a built-in quantization, which is kind of a cool thing to have. Now, in order to expand this into a full-scale sequencer, obviously I'm going to have to add a clock. I'm going to have to add more than one stage. I'll probably add some buttons so that we can turn the quantization on or off. Basically, I'm going to need an awful lot of potentiometers, which seems to be a recurring theme with this analog synthesizer experimentation. So we'll continue with this project probably sometime in the future. For now, I think I've kept you watching long enough, and thank you for that. I'll see you next time.